Hi. Let me show you what we are doing. We were talking about the synthesis of combination circuits. We have examined two methods. One of them is Quinn-McClaskey, the other one is Karnow map method. These are not completely different methods. By using these methods, we are finding the minimal functions for the first canonical form and also second canonical form. And then we examine the steps for these methods. Now what we are doing now, by using these methods, we're going to give some example from practice. We're going to design an adder, and we're going to design a BCD accessory converter. I'm going to explain what it is, and then we're going to give you one practical sub-circuit that we need in practice. So the design of it, I'm going to leave it to you. I'm going to just give you the word description of this one. So let's start with the adder. So let's go to open board, take this down, take this on, and you see there is a transformation to transfer it to open board. Okay, here you are. As we said at the beginning of the synthesis, there is something given to you. What is this? Word description. Let me write this word description. Word description. What is the description of the adder? So we are saying we need a box. We don't know what is inside, but we are saying we are going to apply a number here and another number here. At the output, I would like to get this. So I told you the relation between the input-output. Inputs are the two binary numbers to be added, and output is the sum of those binary adders. So design this box, what is inside. So when this is given to us, we've got to consider all the possible alternatives. So this is the alternatives given here. One of them the serial adder, the other one is parallel adder. So this is not in English, so I can write this English here. Serial adder. What is parallel adder? Parallel adder is this. Assume that you're going to sum two numbers n bit. So x, n bit x number, n bit y number, apply to this, then I can say that the number of inputs is going to be 2n, isn't it? Half n is related with the number x, the other half is related with the number y. So sum of these is going to be n plus 1 outputs. Why is that? Consider small numbers to be added here. So there is now n, in this case is 3 for this number, and this number 3. When you sum them up, 0, 1 is the carry, 0, 1 is another carry, is this one, isn't it? So the sum number is going to be 3 plus 1, so 4 bit. So these outputs, each one of them is a function of these inputs, isn't it? So you can say that the number of inputs is 2n and the number of output is n plus 1 for a serial adder. So we determined now input variables and the output variables. This tells me how many functions I am going to design. n+1 function I am going to design. Each of these functions is going to be the function of 2n variables. So what is inside? We don't know. That's the question mark. Right? So we said this is parallel adder. Why we said parallel adder? Because all these numbers, two numbers, all the bits applied at the same time. But if you consider this summation here, if we do it by hand, we are considering the least significant bits first, isn't it? So this is the least significant bit. So we are adding least significant bits, find the sum and the carry. So that is sum S0, and this is the carry. At the beginning, for least significant bit, the carry bit should be 0. So summation, if you're doing by hand, you are doing the summation each bit at a time, not all the bits. In here, all the bits applied at the same time, but if you do it by hand, you are doing each bit at a time summation. So that is serial. You are applying the x0, y0, least significant bits first, and then x1, y1. It goes like that. At the end, after n operations, you're going to apply xn minus 1, yn minus 1. So that is the serial input. So from this serial input, we are going to get the serial output. What it means, we are going to observe this output, some output first, and then this, and then this, and then this. So what does this mean? We are going to observe the sum number in serial in time. You cannot see all these bits at the same time because there is one output here. At a time, you're going to see just one value. So that is the difference between this parallel adder and the serial adder. How this affects the speed, isn't it? If you apply all the bits at the same time, you get the output in a short time. In serial, if you do it in serial, you're going to wait until this x1 and y1 applied to the system. So that is a bit faster than this one. But in this one, you've got just two inputs. In here, you've got 2n inputs. Whatever the number of bits in your number, this doesn't change because you are applying one by one all the bits of your numbers. On the other hand, you can observe the sum operation. You can observe the sum operation in here, all the bits at the same time, but you cannot observe those here at the same time. So in order, if you consider this serial adder, from the number of inputs and outputs, it seems a bit less than this one. But the thing is, you've got to have some additional elements which are called memory elements. Why do we need that? Because as we said here, when you add those bits, you're going to get a carry. You're going to keep this carry information for the next bits to come. This is the next bits to come, and you're going to keep this carry information in your memory. For this keeping in memory, you need a memory element. So this covers memory element. We haven't seen these. The memory elements included circuits are called sequential circuits. We haven't examined this circuit yet. So we will be doing the designing a combinational circuit design, which is this one. Okay, we have chosen this parallel adder type after we examined the word description. So let's get a bit further now. Okay. How we are going to design that? Now there is a problem here. Okay. What is this problem? I'll tell you. So we said, maybe we can examine. So if you look at this, we've got two n variables. So that is x1 point xn for the number of x, and for number y, we are going to have y1 point yn bits. These are our independent variables. And then we are going to have S0, S1 goes up to Sn, and the last carry. So n number of outputs plus 1. So what does this mean? This is total number of bits. The total number of variables here is 2n. So if you write the truth table for these n plus 1 functions, the number of rows is going to the power 2n. So if n is 5, that means you are adding 5-bit two numbers. The highest could be 31, the other one 31, until 62. The output could be, the highest output could be 62. Then, when you consider the truth table for this adder, parallel adder, so 2 to the power 10 gives you 1024. So that means the number of rows in that truth table, it's going to be this. The number you added, very simple, isn't it? So the highest sum is 62. You cannot add high numbers. If you use the high numbers, so that means your truth table rows increases drastically. So at that stage, we can say that we cannot apply the minimal function realization that we examined already. In order to do that, we should have written all the function and true min terms. For each functions, we've got to group the true min terms. So you're going to compare this 1024 rows just for two simple numbers addition. So if you increase the number of bits of the numbers that you're going to add, you're in trouble. Not practically to do it. Even if you do it in computer, it takes quite a long time, quite a long computer time. So what we could do, we are going to divide it to subgroups. What could be the smallest serial adder? If the numbers that you're going to add, just 1-bit numbers. So that means this, x, y, 1 bit, 2 variables, sum and carry. So this is like that, isn't it? So if I do this, let's come to the next stage now. We can divide it like that, and we can consider, as we have done here, 1, 0, 1. Maybe another one here. Okay. Add those up. So where we're doing the least significant bit carry is going to be 0. Add those up, 0. The carry is 1. Add those up, 0 sum, carry is 1. Add those up, 1, carry is 1. So it is like that. So I can consider this. This is addition of x. This is x0, and this is y0. Least significant bits. Least significant bit. Do not consider this. Don't apply anything. So that's going to be S0. That's going to be C1. So that's the one. So what I am doing here, the C1 is find out at that stage and keep that value to the next stage bits addition. So here you are. The output of the least significant bits carry is going to go to an input of another block this block input is x1 and x2. This is x1, sorry, x1, y1. This is x2, y2. So I can consider now a 3-input circuit. One of the input comes from the previous block carryout, which is this in here, and new bits x1 and 1 addition. So the output of this is going to be the sum, which is this sum, and the carry of this C2 is this, is going to be applied to the next bits, so x2, y2. So this is x2, y2, that's the carry coming to the input of that one, so C2. So when you add those up, this is going to be S0, 1, S1, S2, isn't it? So the output S2, and it goes like that. So what we have done here, we made blocks now. These blocks are repeated. These are the same blocks. At the beginning, the block had got 2 inputs and 2 outputs, but this block has got 3 input and 2 output. So this block is different from this one. So this block is called half adder. And this block is called full adder. So we transferred the problem now from a confusing, complex realization by using the minimal functions to the realization of blocks. These blocks are very simple circuits or very simple functions that we're going to design. So what are these functions? Let's examine these functions now. The first one was the full adder, which had 2 input and 2 output, x, y, s, carry. S comes from sum, C comes from carry. So here is the truth table. These are the functions that I'm going to design. These are the independent variables. These are the bits that I'm going to add up. So okay then, once you wrote it, that's a very simple truth table, isn't it? There aren't so many rows, it's just 4 rows. So the first canonical form of it is like that. That's the first canonical form. For the second function, that's the first canonical form. So corresponding circuit is this, isn't it? 2-level, x prime y, y prime x, edit, you get s, and that's C. That's the first canonical form design. Let's come to this one. We could consider here zeros. If you consider the zeros, what's going to be those? So that means zeros, second canonical form. That means product of sums. What is the sum term for this one? X plus y. What is the sum term for this 0? Is x prime plus y prime. So for the S function, these are the sum functions, and that's the product function. So that's the S. So this is first canonical form. This is second canonical form. In here, I haven't considered second canonical form because if you write the second canonical form for the second function, you're going to have 3 sum terms. That means 3 OR gates, 1 AND gate. So I can consider this function as a sum of products form, not product of sums. In this case, it becomes just 1 gate. So I use this one. This one is the first canonical form. For the S function, I use the second canonical form as well. From the cost point of view, they are almost the same cost, isn't it? So these are the 2 alternatives that we know up to now. But if you use the Boolean function type, then this S function is also an XOR function. XOR function means in practice there is an element XOR element, which is this element, isn't it? So I can use only one XOR gate to get that S, and just one AND gate to get that C. So that is the alternative half-hour design to those. What else we could do? We can play with the Boolean algebra and find alternative circuits. So you could see some functions, you could do some Boolean operations on the functions and get different designs. These are the other two designs. So if you consider now, we've got altogether 5 designs, and our circuit is very simple, so we can play like that. At the end, we could see that this is much better. Why is that? Because the number of gates is just 2 here, and in here it is 3 or more than 3. It's not only the number of gates that we could compare. In those other 4 designs, the level is 2. That means speed is low, isn't it? It's not fast circuit. But if you consider this one, this is just one level. So this is faster than the others. So that is definitely the best solution among those 5. So we designed half adder now. So we said in our circuit, so that one we have done. In our circuit, we've got full adders most of the time. Let's examine the full adder now. This full adder circuit is going to be a simple circuit as well. Why is that? Because we've got only 3 inputs and 2 outputs. So truth table is going to be very simple. Here you are, that truth table. So I can move that. Move that out, sorry. Take this. Here you are. So this is the truth table. 3 inputs, that is the sum, that's the carry. So it is easy to fill up that third table. Why is that? Summation of the 3 zeros gives you 0, no carry. Summation of those 3 bits gives you 1, carry is 0. In here, sum is 1, carry is 0. When you add those up, you're going to get 1 plus 1 is 2, isn't it? 2 is this in binary. So that is the sum, that is carry, isn't it? So for this one, sum is 0, carry 1. For this one, sum is 1, carry 0. For this one, once again, it is like that. There are 2 ones in it. Sum 0, carry 1. For this one also, sum 0, carry 1. If it is 3 ones, when you add them up, you're going to get 3, which is this, isn't it? So that is sum, that is carry. So sum 1, carry 1. So we set up the truth table. So the Carnot map for the S function is this. Carnot map for the C function is this. For this one, there is no any subcube, so you can write as the first canonical form expansion is this, isn't it? Easy. 4 AND gates and 1 OR gate we've got here. But on the other hand, maybe not easy to see for you, but you could check it. This is exclusive OR gate, 3 input exclusive OR gate. For the carry, there are 3 first order subcubes. Each of them has got 2 variables in it. So this is the carry function. So this is the minimal function for this. So when we set up this, so if you do it directly, if you don't use XOR gate, so here you are, you can divide the XOR like that. X and Y XOR and this Z XOR. So this is X XOR Y XOR Z. So it is easy to find this S considering XOR functions. If you don't consider the XOR function, what you're going to have is going to be just 1, 2, 3, 4 AND gates. Each of them has got 3 inputs. And this is going to go into an OR gate of which inputs is just 4. So instead of this, you are using this. Two XOR gates. Each of them has got fan-in is just 2. Simple. So we prefer that, no problem there. But if you do the manipulations, Boolean manipulations on the C function, so let me create this area and clear this area as well. If you do the manipulations, as I said, move that in here. So C function becomes this. So you could do it step by step. It is explained to do all these Boolean operations. So you end up with this. So that's quite interesting. If you look at this one and the S, we've got X, Y XOR. Here we've got X, Y XOR. So which is available here. Output of these XOR is multiplied with Z. Here you are, the Z comes here. So the output of this AND gate is this, isn't it? So if you look at this AND gate, is the multiplication X and Y, which is this. So this is XY. So the C output is the summation of those two. Summation of those two gives you C. S is the XOR. Output of this first XOR is connected to the Z XOR S. So this is this, and that is this. Why we have done all these operations, the answer is here now. So if you remember, that is half adder. That is another half adder. So in the full adder, that was the design of full adder here. Full adder. So in the full adder, I have got two half adders. So half adder 1, half adder 2. We know that these half adder are the simplest realization that we considered already. So two half adders, one OR gate gives me full adder. So that is the full adder that I have chosen. So that is a simple, very simple circuit. This is a very simple circuit. So full adder is also a simple circuit which has got two half adders in it plus an OR gate. So if you consider our design now, so we've got a good solution now. Each full adder here has got two half adders in it. So altogether, total number of half adders is a full adder times 2 plus 1, isn't it? Since these blocks can be repeated as we required, so you can say that if you've got to add m plus 1 number of bits included numbers, you're going to add one more full adder. So you can extend your number to be added by bits. You can extend also your design by adding one full adder. So that means you can adapt any number bit, any bit number included numbers quite easily by adding one more block. So that's a good conclusion. So that's good news. So let's compare now. So what we have done, instead of writing a very long truth table, we divided those smallest blocks and we are using the blocks and we can extend the circuit as we like. In the lab, you have done this realization. If you compare this realization with the previous one, in the previous one you've got XOR gate, AND gate, XOR, AND, and also an OR gate, isn't it? Two full adders, one OR gate we have used for the full adders, and an AND gate is included in the half adder. This also included half adder. So three different types of gates we have used. So in the lab, this reduced to just two. If you look at this circuit now, you've got XOR gate and NAND gate only. So it is just two. So you can compare the results as the number of integrated circuit that you're going to use. As you know, one integrated circuit has got 4 gates if they've got 2 inputs only. So if you consider how many integrated circuit you're going to use for this case, how many integrated circuits you're going to use for this case, this is going to be beneficial in terms of the integrated circuits. That's why we use this circuit in the lab. But full adder, half adder structure hasn't been changed. Only the OR gate removed to an NAND gate, and AND gate has been found out from an AND gate. So you could consider these transitions in this circuit easy to do that. So that is the end of this parallel adder design, and also the end of this video.